Assalamu alaikum. Today we'll discuss the new topic, transient stability. As we know, transient stability is the ability of the system to regain its original steady state or to remain in synchronism after the load change, which is in bulk. We can say load change in bulk. And I have told you this bulk means load change can be fast and load change can be very large. So for the system to be unstable, first we'll discuss unstable. This delta by delta t should be greater than 0, which we have discussed in the last class, that when delta p by delta delta at delta is equal to 0 is less than 0, delta delta by delta t will be greater than 0, which we have seen that like this. It will it will grow on increasing without bound. But if delta delta by delta t is equal to 0, that means here we show it we show its oscillating nature. When delta p by delta delta and delta is greater than 0, it is oscillating in nature, and delta delta by delta t at this point will be 0. When it has some 0, that means maximum value, it means it is then decreasing also. When it's decreasing, for this particular ideal case, when damping is 0, it will remain in sustained oscillation. But with practical case, because our power system will have some damping, it will go on to steady state by decreasing the this amplitude of the damping. This damping in oscillation, amplitude of the oscillation, it will go there. So in general, we can see when delta delta is equal to 0, delta by delta t is equal to 0, the system will be stable. And when delta delta by delta t is greater than 0, for sufficient log time more than 1 second, we can see the system is unstable. Here there is one more thing to be noted down. This delta delta by delta t is the first peak of this delta delta by delta t, because when there is a first peak, that maximum, it then decreases, and the second peak will also be delta delta by delta t is 0, but that peak will be definitely less than this peak. It will go on decreasing. We will not encounter any case when this peak will be greater than this peak. The only case is when delta delta by delta delta by delta t is continuously increasing. There are only two cases which we have already discussed. One more thing, that delta delta by delta t will be 0 when the steady state will occur. But here we are not talking about the steady state, we are talking about the transient state. And in transient state, delta delta by delta t will be 0, means the first maximum. So I want you to make this clear. So a power system has a transient stability if after large sudden disturbance it can regain and maintain the synchronism, which we know. The procedure of determining the stability of a system upon the occurrence of disturbance following by a various switching off and switching on action is called stability study. After the transient system attains the stability when delta delta by delta t is equal to 0, rotor of the alternate neither accelerates nor decelerates. Now there is a difference. This delta delta by delta t uh, refers to the steady state of the system. And at the steady state, delta delta by delta t will be equal to 0, that is shown in the graph. And the earlier delta delta by delta t that is equal to 0, that is pertaining to this maximum. And I hope you understand what does these two things mean, how they are different. And when this occurs, when the steady state occurs, this rotor neither accelerates nor decelerates, but in here it accelerates, here it decelerates, and then accelerates. Here it has both the cases, but here it neither decelerates nor accelerates. So this is about uh, the general consideration about the stability of the system during the transient nature or the transient nature. So I hope you understood the difference between the two delta delta by delta t's. Now let us come to this, that's Equilibria criteria. That this is actually the criteria which is used to find out the transient stability of a system. Usually we can find out by solving the delta from the swing equation, but we know that the swing equation is non-linear in nature. That is very difficult to solve. So instead of solving the swing equation, we can use the equal criteria. This eliminates the calculation of delta from the swing equation, which saves a considerable amount of work and time. That's why we are going to use this instead of the swing equation. This is applicable to single machine connected to an infinite. This is actually a disadvantage because we can use it to two machines also. They are also we have some assumptions, but particularly it is used for the single machine system which is connected to the infinite bus. So it is not used for the multi-machine system. So writing the same equation again, m del square delta by del t square is equal to PA, which is equal to PM minus PE. So del square delta by del t square is equal to PA divided by m. Multiplying both sides by 2 d delta by dt, we get 2 d delta by dt into del square delta by del t square is equal to 2 d delta by dt PA divided by m is equal to twice m PA d delta by dt, because it has to be multiplied. So integrating both sides, we get with respect to dt. When we integrate this with respect to dt, this term, you can see it from here, it comes out to be d delta by dt whole square. When you differentiate this, you can see that it will be twice d delta by dt, 2 times dt, that is 2 times, let's say, x, and then internal differentiation of this will be equal to del square delta by del t square. So this will be integration of this term left hand side with respect to t. Now integration of this term with respect to t, when we integral dt, this dt and dt will cancel out. It means the integration of this term will be equal to 2 by m from delta naught to delta pa d delta. So this is our equation. So d delta by dt will be equal to, since it's square, we can take square root over here. That's 2 by m from delta naught to delta pa d delta. For a system to be stable, d delta by dt should be equal to 0. Change in delta with respect to time should be equal to 0. When we equate this to equal to 0, that means this part should also be equal to 0. You can see it from here. This part is also equal to 0. This is an important result. You can see this is nothing but area under the curve of p delta curve. But this area refers to the area which is between delta naught and delta. This is 0 only when uh, this PA and delta. What is this PA? This PA is actually PM minus PED delta. So it means this will only be 0 when there is some positive part and when there is some negative part. That means we must have some positive accelerating area, because PA is the PM minus P, which is accelerating area, and we must have negative accelerating area or decelerating area. So we can say this area, when it is positive accelerating area, that is PA will be positive, PM minus PA should be equal to negative accelerating area or decelerating area, that is PM minus PE should be negative, and that negative should be equal to this positive. So in general, we can say the system is stable if the area under PA delta curve reduced to 0 between the some values of delta or at some value of delta, that is this delta. So in other words, the system is stable during transient. The positive area, accelerating area, which is the positive area under the P delta curve, must be equal to the negative area, that is negative accelerating area or decelerating area, and hence the name equilibrium criteria for stability. That's why we call it as equilibrium criteria. Now you can see it from this curve. For example, we have a system which is operating at this point, delta naught, earlier in steady state, where PE naught will be equal to PE1, and the system is operating in the the rotor is rotating at a synchronous speed. Now let us say we are suddenly increasing the PM1 mechanical power from here to here. You can see the PE is same, it does not change from here to here. Here we have accelerating power. Rotor accelerates, delta will accelerate from this point to this point. This area which is between PM and this PE, which is the electrical power, because this PM1 has changed from PM1 to PM2. This is the accelerating power because this PM minus PE is positive. This should be equal to, when the delta increases from this point to this point, this is also a area, but this area is a negative area. The system will be stable when this positive area A1 should be equal to this negative area A2. Here it is negative because PE is greater than PM. So when PE is greater than PM, PM minus PE will be negative. So area under this, that is area under this curve, that is this PA from delta 1 to delta 2 should be equal to this PA from delta naught to delta 1. So this is the statement of the equilibrium criteria. So coming to the application of the equilibrium criteria, I haven't explained it properly here because I will do it on this case because it's just application of this. We'll discuss in the application of equilibrium criteria. So the first one, application of equilibrium criteria, is a sudden increase in mechanical load. Before going into this, you should understand this phasor diagram. That means we have already done this. This is the MMF that is created by the rotor. It will be definitely at the rotor, and its speed will be affected by the rotor speed. So in steady state, its speed will be equal to the synchronous speed, and the speed of this FSR will always be equal to the synchronous speed. So let us say our system is operating at point delta naught with mechanical power Pm naught and electrical power Pe naught, which are equal at this point A, and both rotor and this rotor and this will uh, are rotating in a synchronous speed, and delta will be constant, which will be equal to delta naught at this point. So when we increase Pm naught to Pm1, please try to understand this and listen this carefully. Pm naught to Pm1, you can see that now the mechanical power is greater than electrical power at point A. So it means there will be an accelerating power which is available to rotor. Rotor will accelerate. When rotor accelerates, that means FF has got speed which is more than the synchronous speed, and this is rotating at the synchronous speed. When this is rotating more than this, we can see that delta will increase. When delta increases, electrical power increases because electrical power is proportional to sine of delta. When electrical power, and let us say at this point also, you can see mechanical power is greater than electrical power, but the difference between the mechanical and electrical power is less. We can say acceleration will be less, but again acceleration is positive. This FF will be still increasing. We can say at this point, let us say the speed is 1500 rpm. At this point it is 1505 rpm. Here also, since positive accelerating power is there, this will again increase. So when it increases, the speed of this increases, delta will increase, so electrical power further increases. Let us say at point B, you can see further increases till this Pm1 will be equal to PE at this point. So from here to here, you can see there is an accelerating power which is available at the rotor. So rotor will accelerate beyond 1500 rpm. It is an example. So let us say at this point the rotor has accelerated and the speed has increased to 1500 rpm, 1510 rpm, and the acceleration at point B has ceased. There will be no accelerating power at this point. Now beyond this point, you can see that accelerating power is not there, but the speed of the rotor here is 1510 rpm, which is greater than the speed of this, which is 1500 rpm. Delta will still increase beyond this point also. Now at this point, let us say delta increase and electrical power reached over here. At this point electrical power is greater than mechanical power. Now there is a decelerating power available at the rotor. Now the rotor will decelerate. Here the speed was 1510. Let us say here the speed is 1508. Still it is greater than the speed of this. When this happens, delta will still increase, electrical power will again increase, decelerating power will increase. When decelerating power will increase, delta will start decreasing, and it will speed will start decreasing, and it definitely will start decreasing fast. Let us say at this point it is 1504 rpm. Again the speed is more as compared to the synchronous speed. Delta will increase, electrical power will increase, decelerating power will increase, speed will decrease. Let us say at point C the speed of this uh, rotor is 1500 rpm, which is the synchronous speed at point C, synchronous speed, but electrical power at this point is more than mechanical power. Here we can summarize this part, that is the forward. We can see this is from A to C, it is known as forward swing. At point A the speed is synchronous speed, but the power is accelerating power is positive, it accelerates. Let us say at this point speed is 1500 rpm. At this point speed is 1510 rpm. But here mechanical power is equal to electrical power. There will be no accelerating power available. Because of speed of the rotor is more as compared to synchronous speed, delta will continue to increase till point C, but from B to C, speed of the rotor will decrease. Let us say it was 1510, it will come again at point C to the synchronous speed, which is 1500 rpm. Since at point C now, let us see what will happen from C to A, which is known as backward swing. And why would this swings backward, that will also be discussed. At point C, the speed is equal to synchronous speed, but at point C, P is greater than Pm. There is a decelerating power available at the rotor. That means the rotor will decelerate. The speed of the rotor will goes below 1500 rpm. Let us say it goes 1500 rpm. We can say now. Let us say it is 1498 rpm. Now the speed of this phasor is less as compared to speed of this phasor. Now delta will start decreasing. That is why it will go backwards. And when it start decreasing, it will continue to start decrease till point B, because from point C to B we have decelerating power available at the rotor. So the rotor will continue to start decrease at point B. Let us say at point B its speed is 1490 rpm. Now at point B, what will happen? Since the electrical power mechanical power is equal to sorry, they are same and their difference is equal to 0, mechanical accelerating power is not available. But since the speed of the rotor is 1490 rpm, it will continue to decrease. But because speed of this is less than as compared to this, it will continue to decrease. Let us say at point this, the speed of the rotor, when delta decreases, electrical power also decreases. Let us say at point this, when the speed is 1495 rpm, because now the speed increases as compared to this speed, electrical power decreases. There is more accelerating power that is available now at the rotor. It accelerates toward the synchronous speed, and when it accelerates, delta will increase. And when delta increases, electrical power, sorry, delta will not increase because it will increase towards the synchronous speed. Here it is 1495, let us say it is 1498, but if it is still less than this, delta will continue to increase till point A, when the speed of this ff is equal to speed of this, because here acceleration is always available at this point. So at this point, when it reaches point A, the speed is equal to synchronous speed. Here is the accelerating power available. It then starts the forward swing again, which we have already discussed. So from A to B, when mechanical power is changed from this to this, the rotor swings from A to C and then back from C to A. This will continue to do if there is no damping. If there is no damping, which we have shown like this. So the rotor angle will continuously swing. This is delta delta. This may be, will show it. Wait a minute. I am not showing that. So the rotor will continue to swing like this. We can say around point B if there is no damping. If there is a certain damping, you will see that finally when it starts over here, it will go here, and then the swing, it will not come to point A and then not come to point C. This will start slowing down, and then finally settle down to point B. So this is how this happens. But here accelerating area which is available is more, the system will definitely be more stable, because if we increase PM more as compared to this PM1, there are more area, there is more area available, the system we can see is stable. This is the same explanation which I have told you, forward swing, backward swing. Let us try to discuss the summary. Forward swing, when omega is that is the speed of the rotor at point A will be the synchronous speed. Let us say it is 1500 rpm. Speed at B will be greater than synchronous speed. Let us say it is 1510 rpm. Let us say it is point B. Speed at C will be omega s, that is synchronous speed again. PA from A to B will be positive, that's accelerating power. PA from B to C will be negative, that's decelerating power. Delta from A to B will increase, delta from B to C also increase. But here to here, since it is accelerating power is available at the rotor, delta will increase faster. From here to here, this delta B to C will increase slower because there is a decelerating power available. So omega from A to B increases. From here to here it increases. Let us say it goes from 1500 to 1510 rpm. From B to C it decreases. It goes from 1510 to 1500 rpm. That is the speed. Now backward swing. Omega at C is again synchronous speed. Omega at B is less than synchronous speed at this. At backward swing, the speed will be less than, let us say it is 1490 rpm. Omega at A is again equal to 1500 rpm. Accelerating power from C to B, from C to B is negative. Accelerating power from B to A, B to A is positive. Delta from C to B is decreasing, but it decreases faster because we have good amount of decelerating power available. Delta from B to A decreases, but slower. Omega from C to B decreases. Let us say it decreases from 1500 to 1490 rpm. Omega from B to A, omega from B to A increases, and it increases from 1490 to 1500 rpm. You can see back for forward swing, the speed of the rotor from A to C will always be greater than 1500 rpm. 1500 rpm, so it will increase from A to C. Delta will increase from A to C. For forward swing from A to C, the speed of the rotor is always greater than synchronous speed. The speed of this phasor is always greater than this phasor, so delta will continue to increase. For backward swing, the speed of the rotor is less than the speed of this phasor, so it will continue to decrease. That's why from here to here it will swing forward, from here to here it will swing backward. So I hope this is clear to you. Now there are other cases. Let us say we have increased this PM0 to PM2, where this PM2 is greater than PM1. PM1 is the earlier power. So in this case, when the difference of the accelerating power, since PM2 is greater than PM1, that means this PM2 minus PM0 is greater than PM1 minus PM0. So in that case, PM2 minus PE0 is greater than PM1 minus PE0. So that accelerating power available in this case is more as compared to the earlier case. We can say that rotor accelerates to a higher speed in this case as compared to the earlier case. In earlier case, we assume that rotor had accelerated from this point to 1510 rpm. Let us say in this case it increased to 1515 rpm. Now to bring it back to the synchronous speed at this point, so that its swing is back, in this, so that the speed then goes beyond the below the synchronous speed. So it has to bring back this speed. It has to bring back its speed, and it has to go more beyond the earlier value. Earlier value was slightly like this. We can say now the accelerating area is more, decelerating area should also be more, so that this area should be equal to this area. In other words, we say that this delta has to increase further so that this speed will be decreased, because for this case it needs a good amount of decelerating power. So this is the another case. Another case may be when if we further increase PM, a time will come when P delta curve will be shown like this. So we can say the positive area is just equal to the negative area. We can say that at this point it is, let us say, equal to, now when the acceleration is further increased, accelerating area is further increased, so decelerating area has to increase so that it matches to this. We can say this, let us say this is the condition which is known as a critical condition or limiting condition of the stability. At this point, this area, that is the negative area, is equal to this positive area. So when this happens at this point, the speed of the rotor is equal to the synchronous speed, and mechanical power and electrical power is equal, because from this point to this point, since the speed of the rotor is decreasing, and at this point the speed will be synchronous speed in the forward swing, and here mechanical power is equal to electrical power, as instead of earlier case when this speed was equal to synchronous speed but mechanical power was less than the electrical power, it results in decelerating, it results in the further deceleration. But here mechanical power is equal to electrical power. It seems that it should have stopped here because of inertia of the rotor will continue to decrease, rotor speed will continue to decrease, so that when it decreases, angle delta will decrease, and it will result in the backward swing. It will result in the backward swing because delta will then continuously to increase from point C to from point A. And here the reason is that because of the inertia of the rotor. But if mechanical power is increased beyond Pm is equal to Pm3, that is beyond Pm is equal to Pm3, you can see when it increases further at this point. Let us say it is increased at this point. I will show it from here. Now the Pm, let's say 4, it is like this, slightly greater than this. So from, let's say, from point A to point B, which is which is slightly higher than this, the speed of the rotor has gone beyond, let us say 15, 14, 1515, let us say now 1520 rpm. Now since the area is less available for the deceleration from this, at this point when it touches the mechanical power line, at that point mechanical power will be equal to the electrical power. But at that point, the speed of the rotor is still greater than the speed of the synchronous speed. Sorry, synchronous speed. It will continue to decelerate. Sorry, it will continue to accelerate when it continue to after that point, because after that point I can show it over here. Let us say this decelerating power is not equal to this. This decelerating power is less than this power. When, let us say, at this point the speed is 1520 rpm. Now it goes on decreasing, electric power increases, theta decreases, sorry, delta increases, but speed is decreasing. But at this point, since the area is not available much, at this point the speed of the rotor is not equal to the synchronous speed. It is still higher than the synchronous speed. At this point, when it is still higher than the synchronous speed, delta will continue to increase. Delta will continue to increase. When delta continue to increase, you can see it changes from decelerating area to accelerating area. When it changes, because then Pm is greater than Pe naught, it will further increase. The speed of the rotor will further increase. When the speed of the rotor will further increase, delta increases, this also increases. Then the difference of these two increases, accelerating area increases, further acceleration, further acceleration, further acceleration. It results in the further acceleration of the rotor, further increase in the delta, further decrease in the electrical power, further increase in the accelerating power. So in that case, it will lose its synchronism. The speed will go on increasing, it will lose its synchronism, and we see that the system is unstable. If the mechanical power is increased further, Pm is equal to Pm3, it means that the area available for A2 is less in decelerating mode than A1 in accelerating mode, that I have discussed just now. The kinetic energy causes delta to increase beyond point C, and decelerating power change or accelerating power, and system becomes unstable because kinetic energy at this point increases beyond point C. At this point, the speed of the this is the limiting case. I'm talking about the case when Pm is greater than Pm3. At this point, it is not equal to synchronous speed. It is slightly greater than synchronous speed. Delta is continue to increase. When delta increases, Pm increases. But here Pm actually decreases. Pm actually decreases because this is greater than 90 degree. When it decreases, accelerating power also increases. So for this case, when this happens, uh, results in the losing of synchronism. Now for this case, Pm3 is known as transient stability limit, because up to this, when we increase this Pm to Pm3, the system remains stable. Beyond Pm3, it becomes unstable. If Pm is less than Pm naught, and hence delta is so the transient stability limit here will be equal to, because load change is actually the transient stability. Load change is actually here Pm minus P naught. So the transient stability limit for this case is Pm3 minus Pm naught. Now this transient stability would have increased if Pm naught would have been over here. You can see this Pm3 and Pm naught would have been greater. So if Pm is less than Pm naught and hence delta less than delta naught, the transient stability limit would have been greater than Pm3. So which I have, that is actually Pm3 minus greater than Pm3 minus Pm naught. So if Pm is greater than Pm naught and delta is greater than, the transient stability limit would have been less. If Pm is over here. You can see the difference between PM3 and PM0 will be lesser. So in general, we can say that this transient stability limit depends upon this value also, that is the initial operating condition. For delta is equal to 0, for delta is equal to 0, PE is equal to 0, PM is equal to PM0 will also be equal to 0. Then we can have this load change from this point to this point, that is Pmax. The transient stability limit, that is PM3, we can take this PM3 is equal to Pmax. PM3 minus 0 will be PM3, that's Pmax. The transient stability limit would have been Pmax, which is also equal to steady state stability limit, which we have already discussed. So in practical power systems, delta will have some finite value and there will be some PM0. So transient stability limit will definitely be less than steady state stability limit in practical power system. So the transient stability limit depends upon the magnitude of the disturbance. Now, if this magnitude, as I have told you that we have discussed three magnitudes. One is PM1, PM2, and PM3. PM1 is stable, PM2 is also stable, PM3 is uh, critically stability limit. The transient stability depends upon the magnitude of disturbance, and the transient stability depends upon the initial operating condition, that is delta naught. So it depends upon the how bigger is the magnitude of the disturbance and how what is the initial operating condition of the system. Now, for transient stability of synchronous connected to an infinite path, the decelerating area must be greater than the accelerating area. We have just seen it from here. Here, decelerating area is more than accelerating area. Here also decelerating area is more than accelerating area. But here, for limit, definitely they should be equal. More the decelerating area, more is the stability. In general, we can conclude from all these discussion, if the peak of the P delta curve is more will be the steady state stability. If the area under P delta curve is more will be the transient stability. So we can generalize it like this. The steady state stability depends upon the peak of the P delta curve, and the transient stability depends upon the area under the P delta curve. Now from this figure, when we have some times to calculate this, you can see this is symmetrical at this point. So if this is delta 1 from this point to this point, this delta 2 will definitely be equal to pi minus delta 1. That's what I have written over here. Delta 2 is equal to pi minus delta 1. Now PM3 will be equal to because this point will be same as point B. PM3 will be equal to P max sine of delta 1. When delta is equal to delta 1, then P will be equal to PM3. So at this point, P is equal to P max sine of delta 1. So I have written over here delta 2 is equal to pi minus delta 1. PE3 will be equal to P max sine of delta 1. That means delta 1 is equal to sine inverse PM3 divided by P max, and delta 2 is equal to pi minus sine inverse PM3 by P max. These two are important results and they are used to find out the critical angle, that is this delta 2. I hope this is clear to you. I will stop now.